All right. Anyways, as I'm waiting for the notebook to load currently, I'd like to know how the assignment, the lab assignment that was given was for you guys. Like, how did you find it? Was it difficult? Did you face some issues that you like to be addressed, or are there some things from last week that you didn't really get that you would like me to maybe shed some light on? Otherwise, if you're okay or if you're fine so far with everything, you can just give a thumbs up, and then I'll just wait for my notebook to finish loading and then we'll begin the lab shortly. All right, and Michael, you can talk. Yeah, you can talk. You can talk. Michael, you can talk. Ah, okay, okay. Oh, then that's fine. Okay, all right. Okay, okay, that's fine. Well, if you are facing any issues or if you need clarity on anything, you can always send me an email, or if you want my personal number too, I can give that to you anytime you're having any issues, so that it will be easier for you to contact me. Yeah. Anyways, how about you? How about you? Pardon? Michael, you were saying something. You can continue talking. All right. So my notebook is done loading now. So we'll zoom straight into the lab. So for this week's lecture, right? We did norms. We did the norms, the inner product, and then the orthogonality, right? Okay, so basically, so this is the lab tutorial, right, where we are going to show you how to compute norms, compute inner products, and check for orthogonality of a vector or derive certain orthonormal vectors, right, using Python code. So it's going to be somewhat similar to last week's lab session, right? Okay, so the first thing that we are going to do is to talk about the norm of a vector, right? So the norm measures the length, right, or the magnitude of a vector, right? So if you plot a vector on a graph, right, of course it's going to be a straight line, right, at a straight line with an arrow on top. So that's simply a vector, right? So the length of that straight line, right, is ideally the magnitude of the vector, right? So how do we calculate our magnitude? By using a certain formula called there are actually two formulas, right, that you can use to calculate or to find the magnitude or the length of a vector, right? So you can actually calculate the Euclidean norm of a vector, right, which is simply the the square root of the sum of the squares of the individual inputs of the vector, which is shown over here. So at 1.1 Euclidean norm, L2 norms, the Euclidean norm of a vector is defined as, so the vector v, the magnitude of the vector v equals square root of v1 squared plus v2 squared, which is simply the square root of the sum of the squared of each input of the vector, or each entry of the vector, right? So ideally, this is simply like using a ruler, of course, to measure the length of the line of the vector in space. So how do we compute norms in Python using just native Python, right? So ideally for this one, you can using native Python, just like how we did in last week's lab, where we wanted to find the addition, the scalar product, right, and the dot product of vectors, right? We used a Python function. We wrote a certain function which receives inputs, right? Which are what? Vectors. And then based on those inputs, the function is going to compute the addition of those two vectors for you, right? Okay. So for calculating the norm, right? So are going to for calculating the Euclidean norm, specifically the Euclidean norm, which is the L2 norm, right? So we have a function over here. So you write the name of you define so def, like how we did last week, def L2 underscore norm. So L2 underscore norm is the name of the function, right? And to bracket v. So v is a certain argument that you are going to, yeah, you have to satisfy, right, when you are calling that function. So the argument in this case, right, is a vector called v. All right. So we are writing a function L2 norm into bracket v, then put a colon over there. Total equals 0. So you are going to create a variable, right? And then you are going to assign a value of 0 to the total variable. So the variable that we are creating is a total. We are assigning a value of 0 to the total variable, right? Which is shown in the second line. And now we are saying that for x in v. So x refers to any entry, right? Or any component of that particular vector, right? So if we have a vector v, v1 is one component, v2 inside that vector is another component. So for x in v, right? So taking any of the components of the vector, the total plus equals x star star 2. So now in Python, right, when you want to represent, when you want to find the squared of any value, or you want to represent the squared of any value, right? So let's say you want to write maybe 4 squared or x squared, right? You write the base value, right, which is the number which you are finding the squared for. You write that first. So in this case, you want to write x squared, right? So we write x, then star star 2. So now this is simply x squared. This is simply how to write x squared in Python, x star star 2. So now what this function does over here is that it takes the null variable, right, the total variable which has been assigned a value of 0, and then it finds the squared, right, of each it finds the squared of each of the components of that vector, right, and then adds them to the total. So let me break this down for you. So total plus equals x squared, right? What it does is, so first it will take the first component of the vector, which is, let's say, v1, right? Find the square of it, add it to the current value of the total variable, which is 0. So you have v1 squared plus 0, right? So if the vector has, let's say, two elements, right, it will find the square of the first element, add it to the total value, which is 0 right now. So the new total value will be what? X v1 squared, right? Then it will take the second element of that particular vector, right, which is the v2, and find the square of it, and also add it to the new total variable, which became what? V1 squared. So now the final total variable, right, the final value of the total variable is what? X1 v1 squared plus v2 squared, right? And now, and then the function ends at return total star star 0.5. So this is simply the total variable raised to the power 0.5. Now any number raised to the power 0.5 is what? Any number is 0.5 is the same as half. And any number raised to the power half is ideally the square root of that number, right? Or can be written as the square root of that number. So that is what the return line of the L2 norm function is doing. It is finding the square root of the total variable. So ideally, what this function has done is to effectively compute the Euclidean norm, right, of a particular vector. So now let's take an example, right? So v equals 3, 4. So it has a vector with two entries or two components, right? Good. So the vector is v, and now we are going to compute the L2 norm of this particular vector. So you take the function that we've written earlier, which is the L2 underscore norm, and then you pass the vector v, right, as an argument, right, in the function, right, so that it's the function will compute the Euclidean norm. So now let's check this. I'm going to run this cell, and then we'll check the output, right? It's going to take some time because I just started a new, and this is the first cell I'm running. Oh, come on. All right. Okay. All right. I think the cell is still not done running. But then so far, Nelly, are you following? Are you understanding? Have you understood everything I've done so far? I know I've not done much, but I'm just cross checking while I'm waiting for the cell to finish running. Hello, Nelly. Are you still there? You can just give a thumbs up if everything is fine for you so far. You can just type in the chat. Or if you don't mind, you can just unmute your mic and then. All right. Okay, the cell is still taking some time to run. Let me refresh. See if I can. All right. Hello Nelly. Are you still there? Are you following? It's like it's just you and I on the call right now. So I just want to know if you are following before I continue. Yeah. Uh. Oh, okay. Do you think is it from my end or would it be yours? Okay. But are you hearing me clearly now? Can you see my screen? Okay. Okay, then that's fine. So I'm moving on. All right. So what we just did was to so I'm running the cell again where we showed how to find the how to calculate for the Euclidean norm using native Python. Right. So we just wrote a function and I explained. Did you get that part when I explained what the function does and everything? Or you want me to go over it? I should go over it. Okay. So as I said earlier that writing in native Python, right? So just like how we did last week, right? We wrote a function, right, which receives certain um vectors, right, as input, and then it outputs maybe the sum or the scalar multiple a scalar multiple of a particular vector, right? So it's the same thing we are going to do over here. We're going to write a function that calculates the Euclidean norm, right? So this one we are going to use just native Python. We are not going to use any library like the NumPy library we used last week. So now we are writing a function. So writing a function in Python, you have to use a certain word called def, which is def, right? Write the name of your function beside it. Like in this case, the name of our function is what L2 underscore norm. That's the other name for the Euclidean norm. And then we bring a bracket, right? And inside that bracket over here, we write v. So v is the argument, right? Ideally, it should be a vector or a list in this case, right? Because as I said last week, you can represent a vector, right, by a list. Good. So we have def L2 underscore norm brackets v, then bring a colon over there so that Python knows that you are writing or you are writing a function, right? So now, so we create a variable called total and then assign that variable a value of 0. Now you are going to use a for loop. So for loops actually make let's say if you want to perform some kind of task, right, on a list. Let's say you want to add all the elements in a list to all the elements in another list, right, it is more efficient to use a for loop, right? So for x in v, x refers to any component inside a v vector, right, or the v list in this case, because we are using a list to represent a vector. So for x in v, right, total plus equals x star star 2. So x star star in this case, double star, right, means x to the power 2. So that's how you represent, let's say, a value like x squared in Python. So you just have to write x star star 2, and that means x squared. So now we say total plus equals x star star 2. So now what this line of code is going to do is that it's going to take the first element in the v list of in the v vector, right? Let's call that first element v1, right? It's going to find the squared of that element and then add it to the current total variable. So the value of the current total variable is what? 0. So now when you add v1 squared to that 0, it becomes what? Total now equals v1 squared, right? So plus equals, that's the that particular operation over there, adding the v1 squared to the current total value, which is 0. So now the new total value will be what? V1 squared, right? Good. And now since we used a for loop, right, after the for loop is done calculating the v1 squared and now adding it to the total, right, it's going to go to the next element in that particular list, which is what? V2, right? So to find the squared of v2 and now add it to the new total variable value, which is what? Which we stated as what earlier? V1 squared. So now it will add v2 squared, right? So it will become, so now after the loop runs through the whole list, right, it will become v1 squared plus v2 squared, and that will be the final value of the total variable, right? And now the last line of the function says was return total star star 0.5. Of course, 0.5 also refers to half, and you know what the double star means. I mentioned it already. It refers to raised to the power. Now any number raised to the power 0.5 or half is what? Is the same as the square root of that particular number. So now we are finding what? The square root of total, right? And in this case, total was what? V1 squared plus V2 squared, right? Now square root of V1 squared plus V2 squared is ideally the Euclidean norm, right, of the vector V. So now we have an example over here, a vector with entries 3 and 4, right? And then we are going to pass the vector as an argument in the L2 norm function, the function for calculating the Euclidean norm, right? So we pass V inside. Let me run the cell again. Okay, so after using our function, right, to calculate the Euclidean norm of the v vector, right, we can see that the Euclidean norm is what? 5.0. If you take a pen and a paper, or just use a calculator and check it yourself, you would see that that's actually the L2 norm, because we've even done the computations over here, and Python is going to do the whole mathematics behind the scenes, right? So that's our value. So that's one way to calculate for the Euclidean norm. Now we are going to use another way. So you can also use the math library, right? So there's a certain library in Python called the math library, right, which is used for doing normal basic operations, mathematical operations, addition, multiplication, subtraction, square root, yeah, all those things, right? So you can also use the math function. So now we are going to show the math function that has been used to calculate the Euclidean norm of the vector v, right? Okay. So now this is how it's done. So same thing as the previous one, def L2 underscore norm. Then inside, in this case, the argument that we are passing over there is VEC, which refers to the vector, of course. Yeah. So this thing, and then you bring the colon as usual. Oh, good. So now we are changing the name of the variable. Previously we made a variable what? Total. Now you're making it s. So s equals 0.0, right? Now for v in vec, so for any element inside that vector, right, it's similar to the previous one. It's just a change. There's just been a change of the variables, right? So for v in vec, yeah, so for any element in the vector, right, s plus equals, yeah, so I'm coming, yeah, fine, yeah. So for v in vec, yes, so s plus plus equals v star v, right? So it will find, yeah, so this particular one is using a different okay, yeah, it's the same thing. So in this case, we are not doing v squared, right? We are rather v squared is the same as what? V times v. So in this case, we are taking each element, multiplying it by itself, right? Adding it to the s variable, which is 0.0 point 0. So to do that for each element, right? So let's say we have two elements. Let's say v1 and v2, right? So we have v1 times v1. So s will finally be v1 times v1 plus v2 times v2, right? And now we are going to use um um the square root method, right, inside the math function. So to call any method, right, from a function, you write the name of the function dot, then the name of the method that you are calling, then you pass a certain value, right, inside the bracket of the method, right, where you pass the argument. So we have math of square root s. So we want to find the square root of s, right? So math of square root of s, and that will give us this function. We ideally calculate the Euclidean norm using the math function, right? The math library. Yeah. So this is an example. The example that we did earlier, the same vector values that we used earlier. And let's see if it gives us the same answer as the first one, then we are rest assured that this function actually correctly computes the Euclidean norm. So it's giving us the same answer as the previous one, 5.0 and 5.0 again. Okay. So now we are going to use NumPy, right, to calculate the Euclidean norm. So as you can see, NumPy is called the full meaning of NumPy is or numerical Python, right? And ideally, it enables you to perform certain linear algebra calculations much easier and efficiently than if you have to write with native Python, or if you had to use the math library, right? So you import the NumPy library, import NumPy as np, and then now we are going to create a matrix, right? So in using NumPy, while using the NumPy library, you can create a matrix, a vector, right, by using the array method. So np.array, then this is, so you bring a normal bracket, square bracket, then you pass in the element of the vector. In this case, the vector v is ideally 3 and 4. So 3 comma, so first element comma second element, close the square bracket, and then close the normal bracket, right? So now for this line, so this means that you have a vector v of elements 3 and 4. Now, good. So now we are creating a variable called L2 equals np dot lin alg. So we are calling the lin alg method, which is in long linear algebra method, right, from the NumPy library. We're also calling the norm method, right, from the linear algebra method. So now we are calling a method from a method which is also from a library. So np dot linear algebra dot norm, then bring a bracket. So for every method, right, every method is accompanied by a bracket, right, into which you pass certain arguments. Maybe the method is supposed to receive a certain input, then when you run the cell, it will give you a certain output. In this case, the norm method, which is used for calculating the Euclidean norm or the L2 norm, right, receives a vector as an input. So np.linalg.norm into bracket v, which is a vector which we've created, a vector v which we've created, and then print L2 norm. Yes. So let me run the cell and let's see. Same thing, 5.0 as the previous one. So as you can see, right, let's count the number. So as you can see, as compared to the other ways that we calculated for the Euclidean norm, you can see that those other ways made use of more lines of code than the NumPy, right? Than the NumPy library when we use the when we used the NumPy library. So this shows that the NumPy library enables you to efficiently calculate the Euclidean norm, right? Good. So we have a mini exercise over here, but because of time, I will not be able to go over it. Even though it makes use of a vector. So all our examples were vectors with only 2 elements, right? This particular mini exercise makes use of a vector with 3 elements, right? So we can't go through it right now because of time, because time is it's already fast spent. I came into the lab late, so we are going to skip that. But then the notebook will be made available to everyone, so that you guys can actually go through before you attempt the assignment that will be given. All right. So next is the Manhattan norm, right? So which is the L1 norm. So the Manhattan norm of vector is defined as, so Manhattan norm is simply the sum of the absolute values of each of the elements, of all the elements in that vector. So I believe you have a vector v, right, which, let's say, 2 elements. So the 2 elements in vector v was v1 and v2, right? The Manhattan norm of that particular vector, right, is the absolute or the absolute value of v1 plus the absolute value of v2. That's simply it, right? And in this case, for a vector with n entries, right, the Manhattan norm is given as v equals the absolute of v1 plus the absolute of v2 all the way to the absolute of vn, right? Good. So ideally, the Euclidean norm measures the city block distance, right? So in code, the city block distance, in that the Euclidean norm, right? Sorry, I meant to say the Manhattan norm, which is the L1 norm, measures the city block distance. So it traverses like a set of bricks or grid lines, right, before getting to the final destination. But then the Euclidean norm, right, goes through the Pythagorean diagonal, or which is the hypotenuse, right, of a right angle triangle to connect the 2 points. But the Manhattan norm uses a much longer way, right? So it uses the opposite. So you see in a right angle triangle, right, we have the opposite and the adjacent sides of the triangle, right? Yes. So the Manhattan norm uses the opposite and adjacent sides to connect the 2 points, which is longer than if you'd rather use the diagonal, or you'd rather use the hypotenuse, right, to connect the 2 points. Good. So I hope this is well understood. So now let's go to an example to see how you can compute the Manhattan norm or the L1 norm using native Python. So you define a function as usual, create a variable total equals 0, and then create a for loop, right, that loops through the entire vector. So total equals what? So as we said, the Manhattan norm is the sum of the absolute value of each input, right, of the vector, right? Good. So now total plus equals absolute, right, of each. So x refers to any input or any entry in that vector. So total plus equals absolute of x, right? And then you return the total. It's that simple. Calculating the Manhattan norm is very simple. So now let's run this cell and see the value. It says 7. Now we'll compare that with when we use NumPy, right? So for the NumPy, of course, with NumPy, we're able to write more efficient code. We don't have to write as many lines of code as we would have to if we were using the native Python, right? Okay, good. So that's fine. Yeah. So for the NumPy, you just have to create your vector as usual using the NumPy array. So np.array, create a vector, and now you use the sum method, right? So first you have to compute the absolutes, right, of each of the entries in the vector, and then you compute the sum of those absolutes. So that's why we have this line over here. L1 equals np.sum, right? So first thing that is done is what? np.abs. So abs is the absolute method, which is inside the NumPy library, right? So the absolute computes the absolute of any value, right? Good. So I'm assuming that we know what an absolute of a value is. It simply means that it takes just the magnitude of that number. It doesn't take the polarity of the number. So if a number is negative and you find the absolute of that number, right, it just becomes positive, a number without any polarity. So the absolute of -4 is just 4. Yeah. So that was just by the way. So np.abs v, right? So v is the vector, right? So you find the absolute of each of the elements in the vector, and now you sum those absolutes. So np.absolute, find the absolute first, and now you pass the result of that particular just that particular paragraph of code, or just that particular phrase of code, right, as an argument inside the sum function, which will sum the absolute of the individual elements of the vector. So now let's run this and see. So yes, L1 equals the L1 norm of vector v is also 7, like how when we computed with the native Python. Right, good. So now the Euclidean norm, right, can is the Euclidean norm formula, right, is modified to also find the distance, right, between two vectors, right? So ideally, to find the distance between two vectors, you can either use the Euclidean distance or the Manhattan distance, right? So now we are going to look at the Euclidean distance right now. So it's simply the distance between two vectors, or two vectors which are represented by points in space, right? A and B. So we have vector A and vector B. So the Euclidean distance between vector A and B, right, is the first element of A. So square root of the first element of A minus the first, or square root, then so square root of A1 minus B1 all squared, which is what? The difference between the square of the difference between the first element of both vectors plus a2 minus b2 all squared, which is the squared of the difference between the second two elements of both vectors, then all the way to an minus bn. So depending on the dimension of that particular vector space. So if it's a three-dimensional vector space, right, an will end at a3 b3, right, all squared. Yeah. So I'm guessing this is already an answer. So this is just by the way. So now we are going to write a function, right, which computes the Euclidean distance. Right, it's going to be similar to when we're computing the Euclidean norm, but there will be just a small change. Right, so now this function is ideally going to receive two vectors as input, because ideally they are finding the distance between those two vectors. So now def Euclidean underscore distance in the bracket AB. So A is the first vector and B is the second vector. Of course, we know how to write functions in Python already now. So at the end of every function, you have to write and return. Yeah, that's just by the way. So now total equals 0. Now you are going to use a for loop again. So now we are saying that for I in range len A, right? So we are saying that for each element in the vector A, in the vector of length, so len A actually calculates the length of the A vector, which has been represented as a list in this case. So the A vector, right, has been represented as a list. All right, good. And which has what? Two entries, 1 and 2. So now if you compute, or if you use the len function, right, in Python you can use the len function in Python to see the number of elements, or to check for the number of elements in A. And if I'm to run, just let me comment this ones out and just run, just to show you what the len function in Python does. Good. So now let's try it over here. So Control C and then enter. So len of A, the length of A. So run it. Yes, so as I said, the len function will tell you the number of elements inside that particular list or vector. So the number of elements truly is 2, or the number of elements in the A list, right, is 2, of course, yes, as is shown over here. So just by the way also. Good. All right. Yes. So as I was saying, so for I in range the len, so for each element, right, inside the range, which is the length of the vector A, right, take the total, just similar to the other ones we've done earlier. So total, so you create a variable called total and assign it a value of 0, right? Total equals A equals, so A of I. So AI simply means that I refers to the place value, right, of a particular element in each of the vectors, right? So if you are taking so AI simply can take on values from 1 to infinity, right? So if so yes, so AI can be A1 or A2, right? Good. So for I in range blah 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 total plus, so AI minus BI. So what this for loop is going to do is that it's going to take the first element in A, and then also take the first element in vector B, find the difference between them. That's why I have AI minus BI over here. After finding that difference, it will square them. So star star, of course, as I said, it's used to represent what? The square of any value in Python. That's how you write square in Python, right? X squared, as I mentioned earlier. So AI minus BI star star 2, right, or double star 2. So this is going to compute the square of the difference of the first of each of the elements, right, in each of the elements in the two vectors, right? So AI minus BI star star 2. So because it's a for loop, right, it will calculate this for the first two elements, store it in the total variable, go to the second element, right, do the same for the second element in both vectors, and then come and add it, because we did plus equals right over here. So that's what the plus and the equals does over here. So it will take the old value, or that stored inside the total variable, and then add the the value that comes after the plus and equals to the old value, then you get a new value for that particular total variable. Yes. So now After that has been done, right, of course, it's a Euclidean distance. So you have to find the square root of the sum of the differences, right, of the individual elements of both vectors. So now star double star 0.5 is simply square root. Of course, any number raised to the power 0.5 or half is the square root of that number. So yes, so that's what the function does. So now we are going to take an example, two vectors a1 and 2, just like the a1 and 2 and b4 and 6. And now let's compute it. So yes, the Euclidean distance between those two vectors a and b is 5.0. Now we are going to use NumPy. Of course, NumPy is simple and it's fast and it's efficient, right? It uses fewer. NumPy enables us to use fewer lines of code and hence enabling us to save time, right, and work on more important stuff. So a equals np dot array. So you create your vectors, and now you so now for this one you can just use the norm function, right? Instead of going to write a whole long function, the function has already been written for us and is stored in the NumPy library, which and it's also in the method linear algebra. So we'll just use that and then take the two vectors a minus b, run that, of course 5.0. Yes, so we confirm that NumPy is actually good. Yeah, fine. So now let's try to plot, and so that you try and understand, or you will visualize what we just did right now, right? Okay, good. So I'm going to run this. I would have liked to actually take you through how the plotting was done, what each line in the plotting code means, but then there is no time for that right now. But so I'm going to skip. Okay, I'll just take some parts. I'll just skip some parts. So now the plt dot figure, right? So anytime you are going to plot anything in Python, you can use the plt library, right? So it's the matplotlib library, and this time we've imported that library, the matplotlib as plt. So import matplotlib dot pyplot as plt. So we are calling the figure method, right, inside that plt library. We are passing certain arguments. So fixed size is just the size of the graph, right? So we are saying it should be the length. So the first input is what? The length, yes. So the length, and then the second input is the length of the first input is the length of the graph, and the second input is the height of the graph. Yes. And now plt does scatter. So scatter ideally just plots the points. So if you say plt does scatter star a, it is going to take the first vector, which is a over here, and then plot it as a point in the graph, right? So we are doing the same for the vector b, and we pass certain arguments inside that method too. So we've chosen the color blue for the point A and color red for point B. Yes. And then we've labeled it as the following here. So now, yeah. Okay, next thing to is to draw a triangle. Yes. Yeah. So the next thing that is done is to plot this two lines, the broken lines over here, which are the broken lines which are shown in the graph right now over here. So that is what the plt dot plot over here does. So plt dot plot a0 takes the first element in the a vector, right? b0 takes the first element in the b vector, a1 takes the second element in the a vector, and a1 also first element in the a vector. Yes. And then k broken. So we are specifying this, that we want to specify this, that the lines, right, should be broken. So that's what this particular parameter does. Yeah, same for the second one. All right. So now draw the Euclidean distance, of course. So as I said, finding the Euclidean norm is, right, finding the hypotenuse or the vertical distance between the 2 points. That's what I mentioned that earlier. So now we are going to draw this line. So the next line, which is this plt dot plot, draw the Euclidean distance line. It draws that vertical line, right? So a0, b0, a1, b1, yes, and then you color the line green. The color of the line is green, so that's what we have over here. Fine. Yeah, that's fine. Okay. So the rest you can just go and read on it alone. You can just go and find out, or if after the lab or sometime later in the week, if you want me to explain it for you, you can send me an email or something. but because of time, I have to move on. Okay, so now we're also going to compute the Manhattan distance, right? So given two vectors A and B, same vectors, the Manhattan distance, similar to when we're calculating the Manhattan norm, right? It is the sum of the absolute difference, right, between the elements of each vector, right? So simply put, the absolute of the difference between a1 and b1, which are the first elements of vector a and vector b respectively, plus a2 minus b2, so on and so forth. Yeah. So it's also called a taxi cab or city block distance. So as I said, Euclidean is referred to as the Pythagorean distance, right? So you just find the straight line distance between the 2 points. But the Manhattan norm actually finds the Manhattan norm refers to this distance over here, this line. So this line, right, is the line created when you find the Manhattan distance between the 2 points. So ideally, the Manhattan distance between the 2 points is these two lines. Yes. So the opposite and then the adjacent sides of the triangle. Yeah, good. So now let's see, how do we write a function to compute the Manhattan distance in native Python, right? Okay, so write a function, name of the function Manhattan has got distance, create a variable total for I in range length, same as the Euclidean distance, right? So total plus equals, the only thing that changes now is this, right? So previously it was what? AI minus BI all squared, right? Yeah. But in this time it is absolute of AI minus BI, because of course you are finding the absolute of the difference between each of the respective elements of the two vectors, right? So return the total, which will give you the sum of the absolute differences, right, of the each of the elements in the two vectors. So now I'm going to use this function to compute the Manhattan distance between vectors A and B. Right, good. So we call the function Manhattan underscore distance over here and pass the two vectors A and B as arguments, right, inside that function. Right. So of course, all functions in Python receive certain inputs, right, called arguments. So you have to satisfy something called a parameter, right, in the function. Yeah. All right. So I'm running it. So first Manhattan, yeah, so after computing with the function that we just written over here, it says that the Manhattan distance is what? 7. Let's compare that with the Euclidean distance, is what? 5.0. And let's confirm it in the graph. Remember that I said that the Euclidean distance is what? The Euclidean distance is the straight line distance, right? So it's a straight line between the 2 points. So of course, the straight line between the 2 points is going to be much shorter, right, than a line which traverses a whole path or a whole grid of boxes, right, before reaching each of the points. So in this case, that's the Manhattan distance, right? Of course. So graphically, as can be seen in the graph, the Euclidean distance, the green line, I'm moving the mouse pointer over here. Of course, it's going to be shorter than the Manhattan distance, and this is confirmed, right, when we computed the Manhattan and Euclidean distance for the same two vectors. So the Euclidean distance of those two vectors was what? 5.0, and then as expected, the Manhattan distance was what? 7. Good. So we have confirmed what we've seen graphically and analytically, right? Good. Now we're going to use the NumPy. We are going to show how to use the NumPy function or the NumPy library, right, to compute the Manhattan distance. So in this case, we wrote a function instead. Of course, this function is definitely shorter than the previous one if you compare the number of lines in both of them, right? Good. So you create the so this function receives two vectors. Of course, you are finding the Manhattan distance between the two vectors as input, and then in using NumPy, right, you have to create the vectors as an array. So np.array, then the first vector, np.array, the second vector, which is the b, np.sum, of course, just similar to the Euclidean distance. So find the absolute value of the differences between the two, and then sum those absolute values, right? Run the cell is 7. So using NumPy and the analytical Python, they are given equal values here. Good. So this is the plot for the Manhattan distance. So as I said earlier, this is the Manhattan distance, right? which is relatively longer than the Euclidean distance, right? Good. So the plot is similar to what I showed you. The explanation of the plot is similar to what I showed in the Euclidean distance. Let me just explain this part of the plot. So PLT dot title, the title method, right, is where you pass in like the title of the graph which you are plotting. So in this case, you are calling the graph Manhattan distance L1. So we have it over here. PLT.x label is what you want to label the x-axis as. So in this case, we are labeling the x-axis as, of course, intuitively x-axis, which is over here. And then PLT.y label, we are labeling the y label or the y-axis as y-axis, of course, intuitively. So we have y-axis over here. PLT.legend is just, it shouldn't, you can take that out. Now PLT.grade into bracket true, it means you want to show this small grade boxes, right? That's showing over here. If I were to change this input to false, these grid boxes would disappear. Let me run the cell and show you. Yeah, so now we don't have any grid boxes. Now let me set it back to the default value, which is true. So we have the grid boxes again. So PLT dot axis here of equal, yeah, yeah, and then PLT dot show. So this particular line of code, PLT dot show, the show method is very important for you to always put at the end of your entire plotting code, right? Because that's what will really like will make your plot show. Let me comment that out and show you that if you don't bring that, you're going to get an error or your plot will not show. Okay, it actually shows. So anyways, that works anyways. All right, good. Okay, moving on. So we have mini exercises, and of course, I mentioned that we are really pressed for time, so I can't go through the mini exercises now. Good. So now let's see what is the relevance of the Euclidean norm, Manhattan norm, the Euclidean distance, and the Manhattan distance in machine learning? Why are we doing all this mathematics, which is confusing us? What is its relevance in machine learning? Okay. So the L2 norm, which is the Euclidean norm, right, is actually used in gradient-based models, right? So models which use a gradient approach to calculate, let's say, the machine learning models, right, make use of something called errors, right? So error basically refers to or basically describes the level of similarity, right, between a particular prediction and the actual um, label or the actual value, right? So of course, machine learning models are supposed to make predictions, right? So of course, sometimes the predictions may actually deviate from the actual what the actual label is. And now the L2 norm or the L2 distance rather is used to actually calculate the distance between those two values, which is the predicted value and the actual value of that particular prediction, right? Good. And which in turn is used to calculate the error, yes, so the amount of the error, yeah. And now the L1, which is the Manhattan norm and the Manhattan distance, promotes sparsity. So it's used in the selection of features, right? So for feature selection, you are selecting features, right, which very well describe your data, right? So ideally, to select those features, you have to apply some L1 norm or L1 distances, right? Good. So you can go and read more on this in your free time, right? Good. So now the next thing we are going to do is the inner product. So we have the inner product or the dot product, right? Measures how much two vectors are aligned, how similar their directions are, right? So finding the inner product or solving for the inner product of any two vectors, right, will give you a scalar value as a result, right? So now let's look at this. If the inner product is large, it's a large positive value, the vectors point in similar directions. So that's what the after computing the inner product of two vectors, right? If you get that particular scalar value to be a large positive value, then it means that those two vectors are pointing in similar directions. If you get a value of 0, it means that the vectors are orthogonal, meaning they are perpendicular, and it means that they are at right angles to each other. But if you get a negative value, right, for that particular inner product, then it means that the vectors are pointing in completely opposite directions, right? So note, the vectors must, of course, have the same dimensions. If your two vectors do not have the same dimension, then you cannot find the dot product. So you can't find the dot product between a vector with two entries and another vector with three entries, right? Good. So now the dot product of two vectors in the n-dimensional space is defined as this mathematical expression over here. So this is the sum symbol. So this symbol is used to symbolize the summation of certain values. So VIWI. So VI refers to the place value of each of the elements of the vector, right? So I equals 1 all the way to n. Yeah. So you take the first two values of the two vectors, multiply them, right? And then add, and then so take the values, the two vectors with the same place value, right? The two elements of the two vectors of the two respective vectors with the same place value, multiply them, do that for all the elements in both vectors, and then you add the results of the product of those two elements. So for example, let's take the 2D vectors, right? So v1, v2 for the first vector, w1, w2 for the second vector. So the dot product of these two vectors is v1, w1 plus v2 w2. For a 3D vector, it's intuitive, v1 w1 plus v2 w2 plus v3 w3. So now let's see how to calculate the dot product of any two vectors, right? Using native Python. So of course, calculating the dot product, calculating the dot product of two vectors. So of course, our function has to receive two vectors as an input, right? Then to compute the dot product of those two vectors. So total equals 0 for x and y in zip, v1 and v2. So the zip function over here. So the zip function that we are seeing over here, right, is going to combine the two vectors, right? So yeah, the zip function is actually going to combine the two vectors or lay them side by side, right? Good. So for x, so x will be refers to any element in the first or any entry in the first vector, which is v1, and y refers to any entry in the second vector, which is v2. So we are going to use a for loop, right, to loop through the list of the two vectors, which is the v1, which is the zip v1 and v2, right? And then find the product of the first two elements of both vectors and then add that to the subsequent product of the next two vectors, right? And so on and so forth, depending on the size of that particular vector. So in this case, we have total plus equals x star y. So the first, so x star y, of course, as I said, refers to x refers to any element in the first vector, and y refers to any element of entry in the second vector, right? So x star y will take, so the for loop is going to take the first two elements. So to take let's call it v11 and then v21, multiply them and then store that in the total variable, like similar to what we've done so far. So it's going to do that for the entire length of the two vectors, right? And then it's going to return the dot product, right, of is going to return the dot product of the vectors. So let's take an example. We are going to take a vector with three entries, right? So vector v1 three entries, vector v2 three entries. Then we are going to use the dot product function that we have over here, that we've written over here, and then see. Good. So it says the dot product of the two vectors v1 and v2. Yes. Good. Now next, we are going to see how we can compute the dot product of the same two vectors using the NumPy. So of course, create your, in this case, you are going to use a function, right? Of course, this function is relatively shorter than the other function that we wrote earlier. Of course, using NumPy simplifies the whole concept of mathematical doing mathematical computations, right, in Python. So v1, so def dot underscore product dot numpy, that's the name of the function. Inputs takes two inputs, two vectors as inputs, v1 and v2, creates the vectors and then returns the dot product of the two vectors. Of course, you can just use the dot method, right, inside the numpy library. So let's run that cell. Let's take the two vectors and run that cell. Same thing as the previous one, 32, 32. Good. Yeah. So that's fine. So we have another function over here, a dot product, a function that calculates the dot product. All right. But in this case, you are checking something. Remember that I said that you can't, before you can find a dot product of two vectors, right, they must have the same number of entries, or in more technical terms, they must have the same dimensions. So vector A with two entries, right, must before you can find a dot product of, let's say, vector A and vector B, you must ensure that both vector A and vector B have two entries. It's that simple. So now this function, this is similar to the previous function, but in this case, this is similar to the first function that we use to calculate the dot product using a native Python with no NumPy, without the help of the NumPy library. So in this case, you are going to pass a conditional. So a conditional is so in conditionals, right? So you are going to pass a condition inside the function. So we are saying if the length of v is not equal to the length of w, so the exclamation mark and the equal to sign simply means not equal mathematically. That's a mathematical representation of not equal in Python. So if the length of v, so as I said, the number of entries also equals the number, it also equals the length of the vector. So if length v is not equal to length w, then raise value error, the vectors must have the same dimension. So if this conditional holds, it basically means that the vectors do not have the same dimensions, and hence you cannot perform a dot product of the two vectors. So in this case, they have the same dimensions, v and w. Let's run it and see if it will. Yeah, so we have the dot product has been given 11. Now let me change the dimension of v to a three-dimensional vector. Let's then put 6 over here. Good. So as I said, yes. So the vectors must have the same direction. So we got a value error because they had different directions. Yeah, they had different dimensions. So let me restore this back to default. Yeah, that's fine. Okay, moving on. So yes, yeah, okay, good. So now let's also try it with the NumPy. Let me also change. We know the value of the dot product already. Let me change this one too and see. Good. So the shapes of M3 2 are not aligned with. So it basically means that the dimensions of both vectors are not equal. Let me not bore you with the technicalities. Let me change it to normal and run the cell again. Good. That's fine. Good. So now let me tell you one wonderful thing about the dot product. Right? Good. So now let's go through this. So did you know, if you let so if you have a vector, right, v of dimensions n, v1 v2 all the way to n, the dot product of a vector with itself, right, so v dot v, so you are taking v twice, so you are finding the dot product of v and v, so the dot product of two vectors which are the same, they have the same entries, same dimensions, same values of entries and same dimensions, right? The dot product of a vector with itself is what? V dot v, which is what? V1 squared, of course, obviously is v1 squared plus v2 squared plus obviously. And now the Euclidean norm or length of the vector is, so remember the Euclidean norm. The formula for finding a Euclidean norm is what? The Euclidean norm of the vector v was square root of v1 squared plus v2 squared plus all the way to. Therefore, it means that the dot product of a vector with itself equals the square of the Euclidean norm. So it's basically saying that if I should square this function, right, the square is going to cancel the square root over here, and you see that what will be left is equal to what is over here, right? So it basically means that the dot product of a vector with itself, right, equals the square of the Euclidean norm of that same vector. It's that simple. It is that simple. Like it can even be a shortcut you can use to calculate even the Euclidean norm of a vector. So you just find the dot product of that vector with itself, right? And then you find the square root of that dot product of the Euclidean vector with itself. Then that will give you your Euclidean norm. Or if you want to find the dot product, or if you want to find the dot product of that vector with itself, you just have to find the Euclidean norm and then square it, and that's all. Good. So we have an example over here. Yeah. Oh, right. This is an intuitive example, so I'll not really go over it. So of course there are certain axioms, right, or certain rules that inner products have to obey. So now the inner product axioms, let v be a vector space over R. So v is a certain vector, right, of a vector space, right, which is a function, or which is contained, or which is real, right, a real vector space. So it means that all the vectors inside that vector space have entries which are real values, right? So inner product UV. So the you can see this bracket over here. This angled bracket that you have over here is just to represent inner product. So this angled bracket at the beginning and the end over here, containing these two vectors, means that this is the inner product of U and V. So the inner product of U and V must satisfy four properties or axioms. So first, the first condition is that they must be symmetrical. So the dot product of U and V must equal the dot product of V and U. So it basically means that U dot V must equal V dot U, right? And that is kind of like in mathematics, like a commutative property of sorts is basically similar to that, but it's not a commutative, it's a commutative property of sorts. That's how I would put it. So meaning the order of the vectors doesn't matter, right? So, however, wherever you place the vectors, it doesn't matter. If you place V first or you place U first, it doesn't matter. You will still get the same value as if you place U first, or if you place V first, you still get the same value. So, swapping them does not change the result. So, let's take an example over here. So, def, you are writing a function to calculate the dot product, right, of two vectors, right? Good. So, yeah, so I think we know how this it's intuitive how this function works. So def dot product vw return some blah 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 for I in ranges, similar to what we've done previously. You create two vectors, and now the left hand side equals the dot product uv, and right hand side equals the dot product vu. So left hand side equals the right hand side. So in Python, right, if you want to actually check if two values, right, or certain or two certain things are actually very equal, right, in Python you use this particular symbol equal equal. So left hand side is equal equal right hand side. If they are truly equal, right, the output of this particular line of code will be true. If they are not equal, it will be false. So now let's try it. So we are actually confirming this particular axiom of the dot product. So the left hand side use UV, and the right hand side use VU. So we are checking, are they symmetrical? Yes, it's true. So we've confirmed that they're symmetrical. So now we are going to use the NumPy. You know how it works. Then NP dots, yeah. So dot product, of course. If you want to find the dot product of any two vectors in using the NumPy library, NP dot NP bring a period over here, which is the dot, and then you type the dot method, which is the dot, then pass in the two vectors as an argument, which then when you run that particular code, it will find the dot product of those two vectors. So let me run it. Good. So it says the symmetry holds, is true. Good. So we've satisfied the first axiom. So now the second axiom is that there must be linearity in the first argument. So meaning that the scalars and addition can be distributed inside the first argument. The inner product is linear in the first vector, right? All right. So it basically means that if you have three vectors, right, u, v, and w, right, and you have and you have two of those vectors, right, being multiplied by a scalar, right? So you have au, so a is a scalar, right, times u is the vector, plus b, which is also a scalar, times v, which is a vector. So u, v, and w are the vectors, a and b are the scalars, comma w. So it means that the dot product, right, of w and au plus bv must equal this expression over here. So the scalar, so the scalar times the dot product of u and w. So it means that, so the first axiom basically is basically saying that the dot product of au plus bv and w, right, must equal a times the dot product of u and w plus b times the dot product of v and w, right? Good. So now let's try and see if certain vectors actually satisfy this particular axiom. Certain two vectors satisfy this axiom, right? Fine. So we are going to do that over here. Two scalars a and b, which is 2 and minus 1, and three vectors u, v, w, right? So the left hand side, which is this, we are going to compute this particular expression over here. So yes, so the first scalar, so we are going to find the dot product of the first scalar, right, times the first vector plus the second scalar times the second vector, which is the v, for I in range len, comma blah blah blah, for I in range len, comma w. So we are using the dot product function that we wrote earlier. So we are using this dot product function, right, to compute for the dot product between those two. So if we are computing this as I said earlier, and this is the code for computing it. So for I in range, so I know you guys know how the for loop works now, comma w. So dot product between w and all this. That's the left hand side, which is this. And then now the right hand side, which is this, right, is what? A star the dot product of u and w plus b times the dot product of v and w. Let's see if this axiom is actually satisfied. Yes. So yes, it's satisfied over here. So linearity in the first argument holds true. Okay. So now, it has been done using NumPy, and time is actually going to be the time is going to be absent. So let me just skip this part. You guys know how the NumPy array works already. So now we are going to check for positivity, right? So the dot product of a particular vector with itself must never be a negative number. That's what this simply means. It must always be greater than or equal to 0, right? So the inner product of any vector with itself is always a non-negative. It represents the squared length, right? So it's either the dot product of the vector with itself is 0, or it is a value greater than 0. If it is 0, then it means that the vector is a 0 vector simply. Yeah. So let's take a certain vector over here. V equals 3 and minus 4, right? And let's run it and see. So yeah, so dots and we are using the same dot product function that we've written earlier. So inner equals dot underscore product vv. So you are passing the same vector twice, right, inside the argument. And then yeah, so yeah, right. So let me just run it and confirm. So yeah, so the yeah, right, yeah. So yeah, so the dot product of the vector against itself, the dot product of the vector against itself is 25, and then yes, so of course the value is greater than or equal to 0. So yes, it's true. So this is the particular phrase of code. So inner is greater than or equal to 0. So we are asking, is the inner greater than or equal to 0? Then the output over here is true. So that particular axiom of the vector inner product has been satisfied. So now positive definiteness or definiteness. So it basically means that, right, if the dot product of a vector against itself equals 0, then it means that the vector is a 0 vector. It's simply that. So I mentioned that already. Only the 0 vector has 0 length. Yes, so the dot product of a vector against itself, right, is 0. If it's 0, it means that the vector is a 0 vector, so v equals 0. So let's take a particular 0 vector, so v equals 0, and let's do it and see. So yeah, so true, vector is a 0 vector, true. So we've also passed that over here. X equals 0. So we are taking each of the elements. So each element has been represented by x. So yeah, fine. So now let's look at the weighted inner product, right? So in this case, you are doing the normal inner product calculation, all right, but then you're adding certain weights. So the relevance of this in machine learning, right, of the weighted inner product in machine learning is that certain features, of course, features in machine learning are represented by elements in a vector. And of course, certain features represent the data better than others, or certain features are more important than others. And so, to better illustrate the importance of those features, right, you multiply those features or those elements in the vector by a weight. So now let's look at what the weighted inner product does. So some inner products give more importance, as I said, to certain components. So the components in machine learning, the components can refer to the features, right, of the data. Good. So the weighted inner product. Good. So we have the UV, the inner product of U and V times a certain scalar W, right? So WI, UI, VI, so on and so forth. Where WI is greater than 0, it refers to a scalar. So each component is scaled by a positive weight WI, as I said, right? This is useful, as I said, this is useful when some features are considered more important than others. So let's see how the weighted inner product can be computed in Python. So we are creating a function weighted underscore dot products. Of course, inner product is the same as dot product. So weighted underscore dot uv and w. U and v are the two vectors. W is the weight, right? That we are attaching to one of the elements of the dot product of the two vectors here. So for x, y, just like the similar one that we did. So for x, y, and wi in zip, u, v, and w. So as I said, a zip function combines the two lists, right, or the two vectors u, v, and then plus the scalar w. So total equals plus and equal wi times x times y. So it will multiply the weights by the and then return the total. All right. So fine. So of course, the weight is also a vector, right? Good. So now the weight vector contains the value by which you want to scale the particular feature, right? So in this case, we've assigned, so for the first element in the two vectors, right, they are going to be multiplied by a weight of 2. So it means the 1 and 3, the product of 1 and 3 in the dot product computation, right, is going to be multiplied by 2. So we are increasing the importance or the magnitude of that product, right, by 3, which emphasizes its importance, and we're reducing the magnitude of this product, the product of these two components, the second component of both vectors, which is the 2 and 4. We are reducing them by a factor of half, or we are multiplying them by a factor of half, which reduces their importance by half, right? Good. That's what the weighted dot product does. So I'm running this cell again to show exactly what the weighted dot product does. Yeah, hello, can I be heard? Nelly, can you hear me? I think I got disconnected at a point. Where Where did you lose track of the lesson? Was I still on the call when I took the? Was I? Did you? Did we get to the positivity? Did you get that part? The axiom 3A. Can you see my screen? Hello, hello. Can you see my screen? Okay, fine. Hello, can you see my screen? Hello, Nelly. Child, almost done. Fuck you. Okay, okay. Since I know I just got disconnected, but since a recording of the video we made available, I'm going to continue anyways. So I'm just going to take the weighted inner product again, right? Okay, so as I was saying, some inner products give more importance, right? Weight to certain components, right? So if you compute the inner product of two vectors, right? In certain cases, each of the elements, right, of a vector represents a feature in machine learning, right? So let's say you have a vector A. So a vector has two elements, A1 and A2. Element A1 could be of one feature of that particular vector, and A2 is another feature, right? And let's say all we have two vectors. We have two vectors A and B, right? And basically each vector, maybe let's say each vector is a house, right? And then the elements in the vector refer to certain features of the house, let's say such as the number of bedrooms and the number of bathrooms, right? So we are saying that, so let's assume that the number of bedrooms is very important. It's much more important in determining, let's say, the price of the house than the number of bathrooms, right? So to actually illustrate this, right, that's where the weighted inner product comes. So when we find the inner product between those two vectors, let's say a and b, we're going to attach some level of importance, right, to all the first elements. So now computing the inner product, of course, you find two vectors a and b. Each of them have elements a1, a2, and b1, b2 respectively, right? So finding dot product, it will be a1 times b1. So we are saying that all the first elements, right, are more important. So we are going to attach a certain weight to just a certain weight to the first element and another weight to the second element. So because the first element is very important, let's say we multiply the first product of the product of the first two elements by, let's say, a value of 2 to emphasize its importance. So we are doubling its contribution to the dot product, right? Good. And let's say the second element, right, which is eight, the product of the second element of the two vectors, which is what, a2 and b2. So of course we are computing dot product, so it's what, a1 times b1, all of that plus a2 times b2. So now a1 times b1 has already been multiplied by 2, because you know the first elements are very important features. And let's say the second element, right, which is the a2 and b2, right, are less important, so we are going to multiply that also by a weight to emphasize its level of importance, which is less. Of course, they're going to multiply by a weight of, let's say, 0.5, right? And that is going to scale down its contribution to the dot product. So let's see how this is done in Python, right? So we are going to use the def weighted underscore dot function and then pass in three arguments. This is the first vector, the normal vector, the feature vector, first feature vector, which is u, second feature vector, which is v, and then the third vector, which is the weight vector, right? The vector containing the weights, right? Which is the w. So total. So of course, similar to what we've done in the previous functions, right? So for x, y, and wi in zip, so this refers to each of the elements. So x refers to any element in the u vector, y refers to any element in the v vector, wi refers to any element in the w vector, right? In zip, so we are combining all the three vectors, right? So total plus equals wi. So wi is the weight times x times y. So if we've identified that all the first elements of all the first elements of all the vectors are very important, right? Then that means when we are creating the weight vector, right, we are going to assign a very high value, right, to the first element of the weight vector. In this case, in this example, we assign a high value of 2, right? So over here it's going to multiply. So because we are using a for loop, it's going to multiply the first element in the weight vector by the first element of the u vector in the first element of the v vector. So that will be one product plus the second weight, in this case is 0.5, times x. So that is the x is the, in this case x will be the second element of the u vector and y will be the second element of the v vector, right? Yeah. So this is the example we have over here. U is 1 2, v 3 4, and w 2 5, right? All right, that's okay. W is 2 and 0.5. So wait. So the first feature, of course, is more important, as I said, or the first element is more important. That's why we have a weight of 2 over there. So calculating the weighted dot product, let's see what we'll get. I'm facing some network issues. Pass. Okay, gotten a notebook back. Let's move on to the dot product. I'm finding a weighted dot product. So I'm sure you've already gotten everything that the weighted dot product means. Okay, and that's fine. Yeah, the weighted inner product. So we've already been through that. I'm just running a cell for you. So the weighted inner products in this case, then you can calculate that on your own and see. So a unit vector is simply a vector whose length or norm is equal to 1. If v is any non-zero vector, its corresponding unit vector v is given by this. So for finding a unit vector of any vector, right, is to divide that vector by its Euclidean norm, right? So you find the Euclidean norm of that vector and divide each element of that vector by the Euclidean norm of that same vector, and then to give you the unit vector of that vector. So in simple words, divide every component of vector by its norm length to get a new vector that points in the same direction but has a length of 1. Fine. So an example is, let's take vector. So v equals 3, 4. First, compute the L2 norm, the Euclidean norm, alright, which is 5. Now the unit vector is shown over here. So the direction is unchanged, but now the length is 1. Right? The length of the vector is 1. Yeah. So it basically means that yeah, so the length of the vector is simply 1. Yeah. Right. Yeah, moving on. So now let's see how we can find or calculate the unit vector of a particular vector, right? And using code in Python. So we create a function, right, that calculates the L2 or the Euclidean norm of that vector. So it's similar to the functions we've written earlier. So this is common knowledge, we know it already. And now create another function, right, that actually calculates the unit vector of that vector. So def unit underscore vector v. Now norm equals the L2 norm of v, right? Good. So we are storing the L2 norm, right, of the vector, right, inside a certain variable called norm, right? Good. So if the norm is not is equal to 0, right? So meaning it's a, if the norm is equal to 0, meaning that the vector is a 0 vector. Hence, a 0 vector of course has no direction, right? So we can't get a 0 vector does not have a unit vector because it has no direction. And ideally, a unit vector is supposed to show you the direction that the vector is pointing in. right? So if the norm equals 0, right, raise the value error. Zero vector has no direction, of course, and cannot normalize. Good. Else, if the norm is not equal to 0, then calculate the unit vector of the norm, which is of course x divided by the norm for all x in V. So x simply refers to each element in the vector V. So the loop, so this is going to divide each element in the vector V by the norm of the vector. So this is an example using the function that we've just created, the unit underscore vector function. So u equals 3, 4, u equals 3, 4. Good. So let's run it and see what the unit vector of vector v is. Good. So the unit vector is 0.6 and 0.8. So the length, of course, the length of a unit vector is 1.0. That is, if you compute the Euclidean length, right, of this unit vector, right, you get the value of 1, right? Good. So how is this done using the NumPy array? Good. So simply create your vector, and then divide the vector by the norm. Simple. And then this is what you get. So same thing, length is 1.0. So now this is a mini exercise that you can try on your own. So now let's move to the inequality. So the geometric definition of an inner product. So the inner or dot product between two vectors, right, is defined as this. So now we are defining the inner or dot product between two vectors, right, in terms of angles, right? Good. So we are seeing the inner product of two vectors v and w. So the dot product of v and w equals the Euclidean norm of v times the Euclidean norm of w times the Euclidean norm of w cos theta. Yes, good. So where theta is the angle between the two vectors v and w, and v and w are the magnitude or the norms, right, of the vectors. I mean, the dot product measures how much one vector. So simply, the dot product measures how much one vector points in a direction the other. We've already established this. So from the formula to the inequality, so we know that for any real angle theta, right, cos theta falls in between -1 and +1. Simply, cos theta is greater than or equal to -1 and less than or equal to 1. So substitute this into the geometric definition of inner product, right? Good. So it simply means, so this is a geometric definition of inner product, and taking the absolute value of both sides. So taking the absolute of both sides. So we have the absolute of v dot w and the absolute of cos theta, right? And then we know that cos theta is of course less than or equal to 1. It follows that, um, so we have this inequality over here. So based on all those derivations, right, we arrive at this inequality, which is what the absolute, or sorry, the Euclidean norm of the dot product of two vectors should be less than or equal to the product of the Euclidean norm of each of those vectors, right? Good. And this is called the Cauchy-Schwarz inequality, right? Good. Oh, so let's take an example over here and how we can actually test or check if that inequality is satisfied for certain two vectors v and w of elements 2, 3, and 4, 1 respectively. So the left hand side, right, which is this, the absolute, right, sorry, is the absolute of the dot product rather, not the absolute of the dot product rather, not the the Euclidean norm. So it's the absolute. So the absolute of the dot product, which is v and w, right? And that's the left hand side. So we compute that first, then we compute the right hand side, which is what the L2 norm of each of them multiplying each other. Yeah, so the product of the L2 norm of each of the vectors, or the Euclidean norm of each of the vectors. Yeah. So LHS dot 4F. So we are saving, we are we want our answer in 4 decimal places. That's why we have the dot 4F over there. And RHS also in 4 decimal places. So now this is the inequality. We are checking if the left hand side is less than or equal to the right hand side. We are checking if the Cauchy-Schwarz inequality, right, is satisfied for these two vectors. So let's check. And true, it is satisfied. So we have an equality condition. So the equality in the Cauchy-Schwarz inequality happens only when v and w are linearly dependent, right? So it means that if V and W are linearly independent, then this inequality, right, this inequality would have been false, right? This would have been false. So the condition is only satisfied when both vectors are linearly dependent. That is, one is a scalar multiple of the other. Of course, we know what linear dependence is by now. As the vectors are parallel, they move in the same direction, lie on the same line. Yeah. So yeah, so this is what the expression as shows linear dependency or linear dependence. Then the absolute of v dot w equals the the product of the Euclidean norm of each of the vectors. Yeah. So it basically means that for so it basically means that for this to hold, right, V and W must be linearly dependent. For the left hand side to be equal to the right hand side, V and W must be linearly dependent. That's what it basically means. So let's check this over here. So we are taking two vectors, right? And obviously they are linearly dependent because if I multiply vector V by 2 by a scalar of 2, right, I'll be getting vector W. So now let's check this over here. And yes, so you are checking, is the absolute of the left hand side and the right hand side less than 1e minus 9, right? And of course, that's the difference between the two. Is it 0? It's basically asking that. And it's true, yes. So they are equal, and hence it means that they are linearly dependent. So of course, maybe you can also use this to check for to check if two vectors are linearly dependent. So from the cocky swash to triangle inequality. So now that we know this expression, the absolute of v, the absolute of the dot product of v and w must be less than or equal to the product of the Euclidean norms of the two vectors. Good. We can use this to prove that the triangle inequality holds for norms. Yeah, good. So start with this. So v, so the square of the square of the Euclidean norm of the sum of two vectors must equal the dot product of the sum of two vectors against themselves. So it basically means that, yeah, so v plus w, so the sum of the two vectors, and after finding the Euclidean norm of the sum of the two vectors, right, the square of that value must equal v plus w dot v plus w, which is also shown over here, which can also be written in this form or calculated in this form. So this must equal that, which must equal that. So using the Cauchy-Schwarz, right, Schwarz equation, right, we can, using the Cauchy-Schwarz and doing some substitutions and derivations, we can see that v plus w, the Euclidean norm of the sum of the two vectors all squared, must be less than or equal to the sum of the Euclidean norm of each of the vectors all squared. So taking the square root of both sides, then we have this. So this is the triangle inequality, and it states that the Euclidean norm of the sum of two vectors, right, must be less than or equal to the sum of the Euclidean norm of the two vectors, right? Good. Of the Euclidean norms of the two vectors. So let's do this. So this is a function which is used to compute the above inequality, and let's see whether it holds for these two vectors. So yes, it does hold. So the triangle inequality holds. All right. So what I'm basically saying over here is that this geometric formula, right, is what the Cauchy-Schwarz inequality is derived from. Basically, this geometric formula where the dot product of two vectors, right, equals the product of the Euclidean norm of the two vectors times cos theta, right? Theta being the angle between the two vectors, right? Good. So it gives rise to the Cauchy-Schwarz inequality because cosine is always between -1 and 1. So we've been through that already, right? What cosine being between -1 and 1 means for the Cauchy-Schwarz inequality. And once we know that, we can prove the triangle inequality. So from the Cauchy-Schwarz inequality, then the triangle inequality is derived. The mathematical version of the shortest path between 2 points is of course a straight line. We have many exercises which you can do on your own. Now we are going to do the last section of the lab, which is the orthogonal vectors and the orthogonal basis, right? So orthogonality, perpendicularity. So ideally, two vectors v and w are said to be orthogonal if their inner or dot product, right, is ideally zero. Yeah, it's simple. So the dot product of v and w equals zero, and that means that they are orthogonal or perpendicular. Right, good. So they are at right angles, as I said, perpendicular, 90% apart. So they share no directional overlap. Right, good. Or they have no influence on each other. Good. Yeah. So in machine learning, or in other words, you can basically say that they are linearly independent. In other words, or they have no influence on each other. In machine learning, orthogonal vectors represent independent features, zero correlation or no correlation. It's simple, as I said, they are linearly independent. Example from our slide as we showed earlier. So given that we have these two vectors, right, compute the dot product of the two, and it happens that the dot product of the two vectors are zero, hence they are orthogonal. So let's see how we can compute um to check, or you can compute or check if two vectors are orthogonal, right, using Python code. Write a function as usual. Of course, we are checking orthogonality between two vectors, which is v and w. So ideally we will return the dot product of the two equals zero. We are checking, right? Good. So run them and let's see if they are orthogonal. So our v and w are orthogonal, and then the function tells us that true, the v and w with entries 1 and 0 and 0 5 and 5 respectively are actually orthogonal. Now let's see if we use NumPy. So yes, very simple. We have that over there. Yeah, I think this is similar, the same thing. Yeah. So finding orthogonality, and we're also checking if this we're also computing the Euclidean norm for those two vectors over here, and also finding the dot product. And so for finding the dot product, we notice that yes, these two vectors are also the dot product of these two vectors is zero, meaning that they are orthogonal, and they also have each have a Euclidean norm of 1, right? 1.0. Good. So let's use this. Yeah, so the dot product of the unit vectors of the two vectors. Yeah, so these two unit vectors also 0. So meaning, so this suggests the standard basis, right, of any 2D vector space, 1 and 0 and 0 and 1. And of course, they are linearly independent, which means that they definitely have uh, a dot product of 0, right? Hence they are orthogonal. So now let's look at orthogonal basis. So a basis is a set of vectors that can span an entire vector space. By now we should understand what the basis of any vector space means. An orthogonal basis is a basis where every pair of the vectors, right, is orthogonal to each other. For example, take two. So for example, let's say we have three vectors, right, in that particular orthogonal basis, right? It means that, let's say, three sets of vectors, vector a1, vector a, vector b, and vector c. It means that vector a and vector b are perpendicular, vector a and c are perpendicular, and also vector b and c are perpendicular, right? So meaning that that's an orthogonal base, because each of the elements or the vectors in that particular base are perpendicular to each other. So simply put, if you find the dot product between any two elements, right, inside that particular basis, or any two vectors inside that particular basis, you're always going to get 0. Good. So why is this so? It's shown over here. So why is this powerful? Why is this important, or what is the relevance of this? So every orthogonal set of non-zero vectors is automatically linearly dependent. I mentioned this earlier, right? So any two vectors which are orthogonal are by default linearly independent. So orthogonality can also be used as a test for checking for linear independence. So every orthogonal set of non-zero vectors is automatically linearly independent. The coordinates become super easy to compute. They're often just dot products, right? And if you also normalize each vector, you get an orthonormal basis. Same direction, but each has a length of one, of course. So um you find the unit vector of each of the vectors in that basis, right? Yeah, and then yeah. So remember how we found for the unit vectors, dividing each element of the vector by the Euclidean norm, right? So let's see how can we compute for the or check that some two vectors are actually orthogonal basis using a Python function. So we are writing a function is orthogonal underscore basis. So for I in the range, length of vectors, so of course, length vectors will tell you the number of elements in that vector. And then for j in that range, I plus 1, the length of the vectors. All right. So this function is simply going to tell us if or it computes or helps us compute if two vectors or to tell if two vectors are orthogonal bases or not. And are they orthogonal bases? Yes, they are. Of course, these are the default bases for the 2D and vector space 1 and 0 and 0 and 1. Now, orthonormal basis. The orthonormal base is simply an orthogonal basis where every vector has a length of 1, right? Good. So you are taking each vector inside that basis, right? And then you are dividing each element of each vector by their respective Euclidean norms, right? Good. So now the orthogonal have an so first. So let's go back. Let's just revise. Orthogonal have an angle of 90 degrees between the two vectors, and hence it means that they have a dot product of 0. Now for orthonormal vectors, right, they also have an angle of 90 degrees between the vectors, but in this case, each vector has a unit length of 1, of course. If you have a unit vector, right, it basically means that the vector has a length of 1. Good. So now ui, yes, so the length of the unit vector, which is shown over here, equals 1. And then the dot product of one of the unit vectors of the vectors, one of the unit vectors in the basis, the dot product of two unit vectors in the basis, right, equals 0, of course, because they are orthonormal. Good. So why is an orthonormal basis even better? Because calculations become super simple, right? So with orthonormal basis, right, you can represent a particular vector in that space using a linear combination of those orthonormal bases, right? So the dot product becomes the so because calculations become super simple, the dot product becomes the exact coordinate. So if u1 and u2 is orthonormal, so this is a vector space containing these two vectors u1 and u2 which are orthonormal to each other, then c1 equals c1 times v, which is a vector, right? No need to divide by the ui all squared like in a normal orthogonal basis, right? Good. So ideally the orthonormal basis is, of course, its application, we are doing machine learning, of course, so it has an application in machine learning, signal processing, principal component analysis. The principal component analysis is something that is done in something called the finite element analysis, right? It's also using the Fourier basis, the word to vector, etc. Yeah. So it's usually used for making projection, decomposition, and then computation of distances much faster and more numerically stable, ideally. So now let's see how we can check if some two vectors, or check if some vectors are orthonormal basis. So this is the function to do all that. So look through both of the vectors, right? The list of the vectors. Yes, do exactly that. That's what the function does. And let's see. So no, these two vectors, which is 1 dot np dot square root. So 1 divided by the square root of 2 for the first vector, and then 1 divided by the square root of 2, 1 divided by the square root of 2, and 1 divided by the square root of 2. Those are the elements for the first vector. And the second vector, 1 divided by the square root of 2 and minus 1 divided by the square root of 2, right? So we are checking if they are an orthonormal basis, and then it says false, of course. So how the function checks for an orthonormal, it goes through each vector, right, one by one, right, then compares it with every vector including itself, and it performs two tests. So the case, so is the length of the vector 1, of course it has to be a unit vector, right, before it can qualify as an orthonormal basis. And also the dot product, um of those two vectors must be 0 2. Yes, good. So it checks these two cases. Is the length of the vector 1, that means is the dot product of the vector against itself 1, and also is the vector orthogonal with another vector, right? So that means the dot product of the vector against another vector, is it equal to 0? Yes, of course. So that's how you know they are orthogonal, and this is how you know they are normal vector, they are unit vectors, right? Good. So if all these conditions are satisfied, the function returns true. So this function returns true, and it returns false. So it means that for these two vectors, it was not satisfied, and so it will give us an output of false. So yes, so now we have come to the end of the lab. It was a very long lab. If there was anything that you did not understand or you were confused at, you can always send me an email, or if you fancy it, you can request for my personal contact through email, and then I'll provide it to you if that's okay. Anyways, a notebook will be made available, and a recording to this lab session will also be made available. So thank you very much for watching, and then bye. See you next time.